Hey y'all, today we're going to be expanding upon our theory of integration and talking about definite integrals. Now if I ask you to find the area of a triangle, a circle, maybe a square, you'd be able to list off that formula, no problem. What if though, I ask you this question? Given this function in red, let's say it's something like this, would you be able to find the area trapped underneath this curve in this shaded region? It might seem like an impossible task right on the surface. However, what we'll find through this definite integral technique is that you just have to take one integral and you'll be able to figure out this area. So without further ado, let's dive in. Now as I said, this definite integral is going to be intimately connected with area, so it makes sense to start on some areas that we know. But first, a definition. If f of x is a non-negative, meaning above the x-axis or at the x-axis, and continuous on a comma b, the closed interval, then the integral of f of x with respect to x from a to b, so we're tacking on this a and b, this thing right here is going to be defined to be the area of the region bounded by the function f of x and the lines x equals a, vertical line, x equals b, another vertical line, and y equals 0, the x-axis. So this thing right here that I underlined just stands for the area trapped by that region described. As a quick example of what I mean, let's consider the following example. Find the area in green, shaded in green below. So you notice that we have this function y equals 3/2 x. And we have a vertical line at x equals 2. And we're kind of stopping at the vertical line x equals 0. And we're definitely bounded below by the horizontal line y equals 0 or the x-axis. This perfectly fits within this situation above. So I could say the area is just the integral from a, our left-hand point, because it's left over here, well that's left-hand's point is 0, all the way over to where we stop on the right, to of our function 3/2 x, all with respect to x. And that thing will represent the area. Now before we dive into actually how we do that, we notice that it's just a right triangle. So therefore our area is 1/2 times the base of this triangle, length 2, times the height of this triangle, 3. This gives an answer of 6/2, or 3 units squared. We'll actually get into how to evaluate this integral and what it actually means, but right away, what we should understand this as is the area trapped by this region described, so long as f is continuous and non-negative. Now let's talk about the main way that we're going to evaluate these definite integrals. This is actually from the fundamental theorem of calculus, which, as it sounds, is really basic to the study of these integrals. So, let f of x be a non-negative function on the closed interval from a to b. And let's let capital F of x be a function such that f prime of x equals f of x for all x in that interval. So basically, capital F of x is an antiderivative of f of x. Then we have the following. The definite integral from a to b of our small function f of x is actually equal to the antiderivative f with b plugged in it minus the antiderivative with a plugged in it. This is going to be our key way for evaluating these definite integrals. Now that we've got our hands on the fundamental theorem of calculus, we'll actually have a more satisfactory way of dealing with these definite integrals rather than just saying that they are the areas underneath non-negative curves. So, to do this, and first off, let's point out a point of interest. When taking a definite integral, we're allowed to assume that the c from the antiderivative is actually equal to 0. So to see this play out, let's consider the following example, and then we'll come back to this note. So evaluate the definite integral from 0 to 2 of 3/2 x with respect to x. You might notice this from the previous example where we're evaluating the triangle shaded in green. So let's see if our area from the triangle lines up with this definite integral. Copying down the problem, remember that the fundamental theorem of calculus first stated that if you get this type of setup, you need to figure out your antiderivative and then plug in your endpoints to 0. So first and foremost, let's get our antiderivative, capital F. When I antiderive this, add 1 to the power and divide by the power you landed on. That gives me 3/4 x squared, and we're used to tacking on the plus c. Now I'm going to go ahead and draw this evaluation bar. X equals 0 to 2. What this means is that we're going to plug in both 2 and 0. We're going to evaluate between these numbers to our antiderivative. So let's go ahead and do that. The fundamental theorem of calculus states, first off, plug your rightmost endpoint, 2, into your antiderivative. 3/4 times 2 squared plus c. Second, plug in your leftmost endpoint, x equals 0, to your antiderivative. 3/4 times 0 squared plus c. From here, do some simplifying. 2 squared is 4, so what we'll end up with is 4 times 3/4, giving me 3, plus c, minus 0, but then the negative distributes, so we get minus c. Or ultimately, as an answer, we'll get 3, noting that the c's will cancel. It turns out that no matter what your function was, nor no matter what your endpoints are, we're able to cancel these c's out. So oftentimes, whether it be out of laziness or just out of not wanting to write it, it turns out that we don't include c right here. So typically, that will be our next line. 3/4 x squared and leaving off the c because it will ultimately cancel. And notice also something else. These definite integrals, instead of giving you a function as an answer, an antiderivative, they'll give you a number. And if you compare with the last time we did this example, this will definitely match up with the area described before. Let's get into more examples now. As our first non-trivial example, let's go ahead and find the area under the curve y equals x squared plus 4, all divided by x, from x equals 1 to x equals 4. Now it is important to note that this thing is a non-negative function. You can check that via your graphing calculator. So since we're finding the area underneath a non-negative curve, what we can do is state that this area, by the fundamental theorem of calculus, is equal to the integral from your leftmost endpoint 1 to your rightmost endpoint 4 of your function, x squared plus 4 over x, all with respect to x. Now, this is the reason I throw this one on there is that I want you guys to notice that this isn't a U-sub problem. First and foremost, you got to check if you can do your regular rules to it, which we can't, but then you check, can I do any algebra to it? Turns out you can. If I write this as x squared over x plus 4 over x with respect to x, and then go even the step further, writing this as x plus 4 over x dx, kind of simplifying this guy out, we do land on a situation where we can use our basic rules. And also, the other point to doing this right here is to show you that these definite integrals, at their heart, are not really too different than your indefinite integrals in these first stages. So, once we're here, go ahead and compute the antiderivative. Go ahead and integrate it. When we integrate x, we get 1/2 x squared. Add 1 to the power, divide by the power you landed on. The integral of 4 over x, and now we have an x to the negative 1 power, is going to be 4 times the natural log of the absolute value of x. If it helps, remember that 4 over x is equal to 4 times 1 over x. So that we're allowed to factor out that constant and then integrate 1 over x, which we have a rule for. Now if this was an indefinite integral, we would be putting plus c. But remember, that c would ultimately cancel, so all we have to do here is draw this evaluation bar. Evaluated from x equals 1 up to x equals 4. Now we just apply the fundamental theorem of calculus. plug in your top number, 1/2 times 4 squared plus 4 times the natural log of 4. I'm dropping the absolute value bars because 4 is positive, minus this guy with your bottom number plugged in. 1/2 times 1 squared plus 4 times the natural log of 1. Now all you have to do to complete the problem is just simplify this guy out. So notice 4 squared is 16 divided by 2. We'll have an 8 plus 4 times the natural log of 4 minus 1 squared is 1. So we have minus 1/2, but we're distributing this negative. And actually, one thing to point out is that the natural log of 1 becomes 0. So ultimately, that second term that would go right here is just 0. So we would have minus 0. Now last but not least, in order to simplify this out, we would need a common denominator to combine these guys. 16 over 2 minus 1/2 gives me 15 over 2 plus 4 times the natural log of 4. It ain't a pretty answer, but that really is our answer. So if we would have had the c's, they would have just canceled out. That's why we do not include them. But really, these integrals are pretty nice once you know how to actually find an antiderivative of an indefinite integral. Let's get to more examples. Let's talk about this example now. Find the integral from 1 to 3, the definite integral, of the function 6 times the square root of x plus x with respect to x. As always, it's going to be handy to get this thing into fractional power notation. Meaning, write this guy as 6 times x to the 1/2, and then don't forget the plus x and the dx. From here, by the fundamental theorem of calculus, we just need to find the antiderivative. The antiderivative of this, if we add 1 to the power and divide by the power we landed on, will be 6 times 2/3 x to the 3/2. And remember, this 2/3 comes from 1 divided by 3/2. More simply, the integral of just x is 1/2 x squared. Now with a definite integral, we do not include the plus c because it will drop out later, and we just throw in the evaluation bars, 1 from x equals 1 to 3. All we do here, remember, and we could go ahead and simplify this out real quick, 6 times 2 divided by 3, we'll have 12 divided by 3, we'll just have a 4 right here. Make our life a little bit easier. What we can go ahead and do now is plug in the top number to our antiderivative. 4 times 3 to the 3/2 power plus 1/2 times 3 squared, and then plug in the bottom number to your antiderivative. Minus the entire thing of 4 times 1 to the 3/2 power plus 1/2 times 1 squared. Ultimately, now your job is to just simplify and land on a single answer. Yet again, a number. Definite integrals give you numbers. So, as we're simplifying, 3 to the 3/2 power. Well, what we'd end up with is 4, if we just rewrite that. That's the square root of 3 cubed. Well, 3 cubed ends up just being 27. So 4 times the square root of 27 plus 3 squared is 9 divided by 2. So 9/2 minus 4 times 1 to the 3/2 power is just 4. So minus 4. And then yet again, this negative will distribute in. So we'll get minus 1/2. Upon simplifying, that 4 times the square root of 27 ain't really doing anything. We got to leave that as is. But 9/2 minus 1/2 gives me an 8/2 minus 4. But 8/2 is just 4, so we have 4 minus 4. They cancel, and therefore our answer is 4 times the square root of 27. Now one thing I want you to notice about this. Did you see the word area in this problem? It turns out not. So, we could look at these definite integrals as a process totally separate from areas. In fact, we'll have definite integrals that will give you negative numbers if you have a function that isn't non-negative. So really what I want you to be thinking of is a very general process, the process of getting a definite integral, that also has a tie-in to areas in the right context. Now, as we've seen, so long as you can get an antiderivative, we can figure out a definite integral. It might be a pertinent question to consider, what if your integral requires u sub to be solved? Well, this is going to be largely the same, with one little caveat. Given a u sub problem, we must also change our bounds, in this case 0 and 2, into terms of u. The reason for this, and if you think about the evaluation bars on the last problem, are that these numbers, 0 and 2, are in terms of x. When we carry out the u sub process, we're changing this whole integral into terms of u. So these must go too. Let's go ahead and try this problem. Evaluate the integral from 0 to 2 of x divided by 1 plus 4x squared with respect to x. Now, I can't do any algebra. This is definitely not a basic rule, so we need u sub. Let's let u equal the entire bottom. When we do this, in order to get dx out of the picture, we derive, giving me du over dx equals 8x. Now, noting that we want to sub in for dx, we solve for it, giving me dx is equal to du over 8x. Now, how we would proceed if compared to what we've been doing is to therefore plug in. I didn't touch the x on top. I called the entire bottom u, and then I subbed in for dx with this guy. dx equals du over 8x. Or ultimately, what we'd have, once these x's cancel, is the integral 1/8 times du over u. Now notice I've left off 0 and 2. These guys were in terms of x. I need them in terms of u. In order to do that, what we're going to do is actually plug in 0 and 2 into this thing right here. I've described these guys as your translators, and no word is really better. For instance, if I plug in 0 for x, I can get some number in terms of u. So in order to figure out the bottom bound, u sub b, plug in 0 into your u function. 1 plus 4 times 0 squared, which just gives you an answer of 1. That means I'm going to replace this number 0 with the number 1, where 1 is in terms of u. Now to replace 2, to get our top number, plug in 2 for this function right here. 1 plus 4 times 2 squared. 2 squared is just 4. 4 times 4 is 16, plus 1 is 17. So now my top number is 17, and my bottom number is 1. Now we have absolutely everything in terms of u. And now we can actually integrate. So, when we integrate, the 1/8 can be pulled out front. The integral of 1 over u times du, so remember, du over u, if you don't like that notation, can be written as 1 over u du. That will just give me the natural log of the absolute value of u. We don't include the plus c because we have a definite integral. Instead, we draw the evaluation bars from u equals 1 up to 17. Now the nice thing, this is paying a little bit forward. For instance, we have to do this algebra, kind of stinks, but notice something over here. These numbers are in terms of u. We don't have to plug back in for x, for what u was, since we are just going to plug in these numbers. So therefore, all we do to solve the problem is plug in 17 for u, since that is in terms of u. We'll get 1/8 times the natural log of 17, and subtract away 1/8 times the natural log of 1. Plugging in the bottom number. Last but not least, notice that the natural log of 1 is just 0, leaving me with a final answer of 1/8 times the natural log of 17. We'll go over one more u sub example, but remember, if you convert these numbers into terms of u by plugging in your x values to this function right here, you actually don't have to plug back in for x, since we're just going to be plugging in these numbers for u since they are in terms of u. Let's evaluate the following example. Determine the integral from 0 to 1 of e to the 2x times the square root of e to the 2x plus 1. Now before we even go, we've always known that a fractional power is better than root notation, so immediately I convert to that. Now I can't do any algebra because I can't really expand this out with that 1/2 power, so therefore this is a u sub problem. So we are now committed to converting everything into terms of u. Let's call u to be the thing trapped by the power. Always a pretty good option. Noting that I want to sub in for dx, I get a dx in the picture by deriving u. The derivative of e to the 2x is the derivative of the power, 2, times the original function, e to the 2x. And then the derivative of 1 just becomes 0. This ultimately gives me, when I multiply up and divide over, that dx is equal to du over 2 times e to the 2x. And these two lines right here give me my translator. Now, since this is a definite integral, we have two more things to translate. These numbers, 0 and 1, are in terms of x. So in order to get them into terms of u, we plug them in to our original function. So the bottom number, 0, all we do is plug it in right here. E to the 2 times 0 plus 1. That will give me my bottom number, the number I'm going to sub in for 0. Well, e to the 0 power is just 1, so we get an answer of 2. So 2 is my bottom number, and hence the sub b. My top number I determined by plugging in 1 to where x is in this line. So I get e to the 2 times 1 plus 1, which unfortunately can't be really simplified out. We just get e squared plus 1. And now these numbers are in terms of u. From here, carry on as normal. I didn't touch that first e to the 2x, so I copy that down. I call this entire thing u, so times u to the 1/2, and then ultimately I sub in for dx with du divided by 2 e to the 2x. It looks a little bit too much like a v for me. This gives me, upon canceling out these guys right here, the integral from 2 up to e squared plus 1 of our 1/2 times u to the 1/2, all with respect to u. Now that this is in a simple form, we go ahead and integrate it. Allow me to box this off real quick. When I integrate this, I add 1 to the power, u to the 3/2, and I divide by the power I landed on, 2/3. I don't include the plus c because it's a definite integral. But lastly, I evaluate from u equals 2 up to u equals x or e squared plus 1. Now all we have to do is plug in for u, since these were already in terms of u. This gives me ultimately, upon realizing that this just cancels to be 1/3, the 2's cancel out nicely, that all I just have is 1/3 times e squared plus 1 to the 3/2, so I plugged in for u, minus 1/3 times 2 to the 3/2 power. So I plugged in for 2 now, 2 for u. This guy doesn't really simplify down too much since we just have 3/2 powers, so that will go ahead and be our answer. So U sub isn't too bad with this definite integral theory. However, we just have to recognize you got to transform everything in the integral into terms of U, including these numbers, which are originally in terms of x, by just plugging them in to this guy right here, as seen below. Now we're going to kick our talk of area until the next section. However, I did want to talk about something that's a little bit more general. Definite integrals are actually going to be the language of accumulation. Now what do I mean by this as far as this chapter goes? I mean that a definite integral from a to b of a lowercase f of x dx is actually going to tell us about the total amount accumulated by your antiderivative, capital F of x, from x equals a to x equals b. Now as far as business goes, this means if I give you a marginal cost, a marginal revenue, a marginal profit, some lowercase f of x, that you could tell me something about its antiderivative. In the context of marginal cost, marginal profit, or marginal revenue, the antiderivative is total cost, total profit, or total revenue respectively. With that in mind, let's consider the following example. Find the total revenue accumulated from x equals 5 to x equals 9 units. So emphasis on total. We're talking about just the revenue function in that above line. From x equals 5 to x equals 9 units, if the marginal revenue is given by dr over dx equals 1/2 x to the negative 1/2. Now key words. We're given a marginal and we're curious about a total. In order to go back up the ladder, we need to antiderive. Last but not least, accumulated. That tells me I need a definite integral. So the total amount accumulated, so total revenue accumulated will be given by the integral, kind of as above, from 5 to 9 of my marginal revenue. Well, this is just a definite integral. Let's go ahead and solve it. I add 1 to the power, giving me x to the 1/2, and I divide by the power I landed on, and I'm left with kind of a nice function, x to the 1/2. Solved from x equals 5 up to x equals 9. Just as normal, and by the way, real quick, this is my total revenue function, x 1/2. So now, we just treat this as normal. Plug in your top number, so we get 9 to the 1/2, and we subtract it from the bottom number plugged in, minus 5 to the 1/2. Ultimately leaving us with kind of a non-satisfactory answer. 9 simplifies to 3, and then 5 doesn't really simplify down, so we get 3 minus square root of 5. Now really what I want you to be thinking of, since this is your total revenue function, is you're just plugging in 9 to your total revenue function, right here. That will just give you the revenue that you have achieved after making 9 units. Similarly, this will just give you the revenue you achieved after making 5 units. So this thing right here really is telling you how much revenue did you gain from x equals 5 units to x equals 9 units. And we could do that with just a regular antiderivative, with a definite integral. So this thing right here is actually going to be an answer given in dollars. So 3 minus the square root of $5 will ultimately be your answer for this problem. Hey y'all, thanks for tuning in today as we explored the concept of definite integrals. As a recap, in order to take a definite integral, say the integral from a to b of f of x with respect to x, you first off anti-differentiate as normal and get your hands on a function capital F of x. Now you don't need to include the plus c as it's going to cancel out later, but instead all you need to do is evaluate capital F of b minus capital F of a. In our exploration of the topic, this will always give you a number. So if you land on a function, you probably did something wrong. You should get a number with these types of things as far as we're concerned in our class. Last but not least, these definite integrals often deal with area. However, they more generally deal with accumulation. We'll dive into area and kind of more of an exploration of that topic in the next section. But for now, just focus on getting your hands used to the process of finding these finding these definite integrals. So go ahead and try all your homework, email me with any questions, and as always, good luck.